Hello, I hope this video finds you well. Today we want to work with the problem called remove the kth node from the end, or in fact, I think this problem in particular uses n. But the idea here is that the parameter for the method responsible for executing this implementation is that they will give you a variable n, which can be initialized to, let's say, 3, for instance. And so the idea here is that we want to count down 3 from the end of the linked list and essentially remove the nth element or the kth element. So we would so this would be one element. This would be the second element. This would be the third. And so we'd want to remove the nth element, which in this case is the third element. So our linked list should essentially return back emd dy instead of the linked list that includes I. And so the basic approach in terms of deleting a node is that we're not so concerned about the node that we're deleting as much as we're concerned about the nodes that surround it. And of course, by nodes, I mean these actual objects which store the value and data. We call them nodes, but the nodes in terms of Java are really references to these locations. They're not these locations themselves. But the idea here is that if we wanted to delete the third element from the end, we would want to have a reference attached to this node. And let's say this reference was D. And we would then say D.next equals D.next dot next. And so what this would do is it would access D's next property, which is essentially allowing us to refer to the next element in line in terms of the linked list. And it would essentially take its reference. So the dot next part is actually this, it's D's hand in a way that's reaching out to the next node. And so instead of D's dot next referring to L or I, I'm not too sure, we would essentially bridge the gap between this D and this D, and we'd essentially have it refer to D dot next dot next. So that's the basic approach in terms of having a linked list, having a node in the linked list sort of garbage collected. And so we want to implement that, but the problem comes down to being able to figure out what the third element or what the kth or nth element is from the end of the linked list. So that's always the issue of concern throughout this problem. Once we have that, I'm sure we could find some way to implement that detail. Sort of coming into a solution here, we're first going to worry about finding the nth element, and then we'll see how we can remove it. In most linked list questions actually follow the two-pointer approach, and this one is no exception to that pattern. The idea here is that we'll have one pointer, and we'll have another pointer as well. And we'll call one fast, or this one we'll call slow, and this one we'll call fast. And so the idea here is that initially they're both pointing to the same node or object, and what we do is we increment fast by 1, and slow is essentially lagging behind fast. Now, fast at an initial stage actually is buried nth nodes into the list. So whatever n is will bury fast nth nodes into the list. So if n was, let's say, 3, like we took in our example, we'll have 1, 2, 3. And then we would follow this process of incrementing both of these references by 1 in tandem or alongside each other. And by the time fast gets to null, slow would have been pointing to where we wanted to be. So you can see here that if we increment both by 1 on each iteration, by the time fast is null, slow would have essentially landed on the nth node from the end. And we can test this out with various cases. For instance, if n was 2, we would bury fast 2 nodes into the linked list starting from the beginning. So we would say 1, 2. And as we would increment both in tandem, we would see that slow, by the time fast hits null, slow would have been 2 nodes from the end, which is what we wanted. So we would say, we would increment both by 1, and we would do that again, and we would do that again. And now fast is null, and slow actually points to the second node from the end of the linked list. Now, we've been able to find the nth node, and the logic for that is probably not too difficult to wrap our heads around, specifically because we would, we would have 2 pointers. We would create references here, and we would have a while loop, and the while loop would essentially say, while fast is not null, keep incrementing fast by 1 and slow by 1. So we would do fast equals fast.next, and we would do slow equals slow.next, right? And that would essentially, but by the time the break condition is satisfied, by the time fast is null, we would have effectively figured out the kth node from the end. And so that's the 2-pointer approach in terms of finding the kth node. But recall that our goal was essentially to remove the kth node. And I think I prefaced this process by saying that removing a particular node we're not really concerned with the node in particular as much as we are with the nodes that surround it. And if we wanted to remove the node that is being referenced by slow at this period in time, we would have to bridge the gap between the node, essentially its predecessor and its successor. So I and y in this case. And so if an intuitive analysis here, an observation is that if we would have repeated this process and kept everything else the same with just slow lagging behind by 1, we could say that slow equals slow.next, or we could say that currently slow's next is this hand here. And slow.next, what is slow.next pointing to? Slow.next is pointing to D, right? But we want to take this hand and we want to extend it over D, which is the nth node, the second node from the end, and we want to extend it to Y. So slow.next should ideally point to Y, or to this particular node. But of course, there isn't a reference that we've stored for this particular node. So what we can do is we can say slow.next is equal to slow.next, right? So we're saying slow.next, its hand, is equal to slow.next, next. And then that would effectively get us that, it would allow us to essentially bridge the gap between I and Y, or these nodes that I'm referring to. So really the argument here is that if we kept everything in this process the same and all the logic consistent, all we would need to do is offset slow by 1, right? So we would have we would have both of these pointers exactly the way we wanted it to when n is, let's say, 2. So n is 2. We would do everything the same, right? We would bury fast 2 inside the linked list. So we'd say 1, 2, and then we would increment by 1, right, each time. So 1, 2, 3, and then 4. And now fast is null and slow is on the second node from the end. And so that works out. But we want to offset this process. We want to offset slow by 1. We want it to lag behind fast 1 more than it already is. And the idea behind that is introducing a dummy node. So we're going to, in our code, essentially what we're going to do is we're going to invent a we're going to have another node derived from the node class, which is going to be called dummy. And we're going to essentially set it equal to, it's going to be an actual object, and we're going to have it as -1. And the idea here is that if we have this dummy node, then starting these 2 pointers at the dummy node and keeping fast the same distance from slow as was before, once we would increment 1 by 1, when fast is null, it would be 1 behind the node that we want to be on, or the node that we would want to delete. So this allows us to offset slow by 1, and it allows us to then say that slow.next equals slow.next.next, right? So that it allows us to do this. So finding the kth node is a matter of starting them both from the head of the list and then burying fast n nodes into the list. So if it were 3, then we would do 3 nodes into the list. And then if we were to move slow and fast in tandem, we would essentially, when fast is null, it would be 3 nodes into the list. So that's the idea. But if we want to delete the 3rd node, we'd actually start from slow, right? And we would start from slow, we would bury fast 1, 2, 3 into the list. And then we would repeat the same process. They would both move in tandem. And then when fast hits, it would essentially be 1 before where we'd want it to be. So I don't think this was done right here. So we have 1, 2, 3, and so this gets moved this way, and then it gets moved this way, and it gets moved this way, and then it gets moved this way. And so ideally it should be here. I'm not too sure why that isn't the case. So if n were 3, so if it's 1, 2, 3, right? We want to keep it the same place where it was had we had slow at the head, right? We don't want to recalibrate fast just because we've added this head. We simply want to offset slow. So if I buried fast 3 nodes into the list, 1, 2, 3, when slow was at its head, all I want to do is offset slow. I don't want to offset fast as well. I want to keep fast in the same position as if slow were at its head. You know, in this scenario, when slow is at its head, fast should be where it would have been had we followed simply finding the nth node. And then when it comes to removing the nth node, we simply want to offset slow by 1. We don't want to offset fast by 1. So in a way, we want to, if both fast and slow start at the dummy node, we want to bury fast n nodes into the list plus 1. And then when we increment both of these pointers, you'll see that when fast is null, we're right behind the 3rd node from the end. And that would allow us to do slow.next equals slow.next.next. And that would effectively allow us to extend this reference's hand over the 3rd node and then delete the node in question. And so this is our dummy node here that we've created. And in terms of returning the head of the list, we can just do dummy.next. Okay, and just do dummy.next. And so that is the idea there. And so now, in terms of implementing the code, I want to be able to show this while the picture is still up. I don't want to go rigidly into the code just yet. I want to be able to do this side by side, just so that it's more clear. So our current situation is that we have a list, of course, and what we're going to do, let me see if I can do this a little better here. Right. So what we're going to do here is we're going to have, so let me go ahead and grab the method that that is being used for this particular problem. So this is the method here, and of course we have our head and we have an integer n, which is going to be the nth node from the end. So initially we start by creating that dummy node, right? So in this case, it's not called node, it's called list node, but it's actually the same thing. So we're going to call it dummy, and we're going to set it equal to the head. And so what that's going to do is it's going to create, it's essentially going to create this new node called dummy, which is what, we want to first create that object first, that dummy object. It doesn't actually exist yet before we instantiate it. So we're going to say list node dummy equals new list node, and we'll say that it's -1. So we've created a dummy node here that is essentially, so this is now dummy, okay? And let me actually put this at the top here so it's not as confusing, but this is dummy, okay? And dummy is initialized to -1, but it doesn't have a .next property yet. We haven't done that yet. It just exists, right? And then when we want to essentially point it to the head, so this is the head. So we'll say that what we'll go and do here is we'll say dummy.next, which will allow us to access its next property, will essentially equal the head of the list, right? And then once that's once we've been able to situate that, what we can do now is we can update our list here. So now it's successfully at the first. And so you'll remember that I wanted to start fast and slow at the beginning of the list. And so what I'm going to do is I'm going to instantiate or create those references. So it derives from the list node class, and I'm going to call it slow. And I'm going to essentially point it to dummy, which is pointing to the head. So that's an equivalent statement. And I'll do the same thing for fast, and I'll point it to dummy as well. So that's what we're looking like at the moment. Now you'll remember that we want to bury fast k nodes into the, or n nodes into the list, but we want to do it as though the dummy doesn't exist. So if slow were here and if this were the head, then we would bury fast n nodes into the list. We would do 1, 2, 3 in the case that n is 3. In that, and we'd leave it at that. But since we want to be one behind, since we want to offset slow, all we're going to do is offset slow. So really, if fast and slow are going to start at the dummy, we want to have fast n nodes into the list plus 1. Okay, so we want to have n nodes. So fast should be at n nodes into the list. So 3 nodes, 1, 2, 3 into the list plus 1 in order for this to work. So we're going to essentially do that here. We're going to have a for loop, and we're going to say we want to move fast n times, right? But not just n, we want to move it n plus 1 times, and we're going to increment I each time we do this. And now we're essentially going to say fast will equal fast.next. So for each iteration, the fast reference is going to equal what its subsequent node is, what its successor is. And so this allows us to implement that. And now we can move slow and fast in tandem, right? We can have them move together, and then when fast is null, slow will be one behind the nth node from the end of the list, which is in fact just the third node from the end of the list. And so we'll say that while fast does not equal null, we're going to move both in tandem, right? So we're going to say fast equals fast.next and slow equals slow.next. And so that helps us achieve that. And after, so by the time we get to this part in the code, slow is one behind the nth node in the list, which is in this case the third node. And what we want to do at this point is we want to take what we want to take slow's next property, which is currently pointing to this node, and we want to extend it over to the successor, or the successor times 2, slow's successor times 2. So slow's successor is this, and then its successor is that. So it's sort of like slow's child's child in a way. So we want to do slow equals slow dot next. We're going to access its slow's. We're going to access slow's next property, and we're going to say slow dot next will equal slow dot next, right? And that's going to get us to that point. So we're going to say, so by the time the loop ends, we'd have been one behind the element that we want to be. And so we'll say slow equals slow dot, well, we'll say slow dot next equals slow dot next dot next. We want to access its next property, and then set it to double that. And then this node here would have just been out of the question. And then in terms of returning the head, now that we've found and deleted the kth node, well, the head is not a particular node. We just passed it in as a parameter, but dummy.next is referring to head. So we're going to say, we're essentially going to return dummy.next, okay, as the head. And so let's go ahead and hop into the code here. So we're going to create that list node dummy, and we're going to essentially list node dummy equals new list node, and we're going to say that it's -1, and then we're going to create list node fast equal. It's going to be set to dummy as we mentioned before, and list node slow is also going to be set to dummy, and then we're going to essentially have fast move n+1 times deep into the list, and then in order to get that to work, we're going to say fast equals fast.next, and then once we've moved fast n+1 nodes into the list, we're essentially going to have a while loop which states while fast does not reach the end of the list, or while it's not null, we're going to move both in tandem. So fast will equal fast.next, and slow will equal slow.next. And after that's said and done, we'd have been one node behind the node we want to delete. And so we're going to extend slow. Slow will actually reference that element, which is one behind the element we want to delete. And so we're going to access slow's next property and set it to slow.next.next. And then we'll just return the head of the list, which can be referenced by dummy.next. I guess we have to sign in here, but this should be the code.